Howdy, howdy, folks. Welcome to Psych 652 Lab, Module 12, where we're going to be discussing factorial ANOVAs. So, for our objectives for today is I'm just going to give you a quick rundown of what a factorial ANOVA is. I'm going to do a description of our data set so we know what we're working with, and then we'll do our classic coding tutorial. So factorial ANOVA is pretty similar to what we were doing last week, which was that one-way ANOVA, except now we have two or more independent variables that are categorical in nature. So here we'll be analyzing if the levels of our IVs differ, and additionally analyzing if the interaction between those IVs differ as well. And essentially what an interaction effect is saying is, does the slopes between our two groups differ? And I think this image does a really good job of explaining it. As you can see, people with low self-esteem have different experiences with success and failure in terms of attribution to self as compared to people with high self-esteem. So whether you're high self-esteem or low self-esteem really matters about how your attribution to self will be affected when you are faced with outcome of success or failure, essentially, is really what we need to focus on here. So notice how the slopes differ dramatically, and that would be an indication of a interaction effect. And to talk about what data we're using, just because we've never used it before, this is a diet data set that I found online, which compares different diets and outcome variable of how much weight was lost after 10 weeks of using the diet. So essentially the main variables of interest that we're going to be focusing on today is the gender variable, which is a categorical variable in which 1 equals male and 0 equals female. And then the diet variable, which is one of three diets, which is the control condition, an Atkins diet, or a Nutrisystem diet. And then lastly, our outcome variable is going to be weight loss after the 10-week diet loss program. Okay, so let's go ahead and start coding. Okay, so go ahead and just do some deletion here so we can get set up. Okay, so first thing we're going to do is we're going to go ahead and open up RStudio. Okay, we're going to go ahead and create a new project, a new directory, new project, and we're going to name this module 12. Make sure it's saved in that correct subdirectory, and create that project. And there we go. And then we're going to go and download that diet data set that I explained earlier. So we'll go to modules, run down to module 12 lab. Download that diet.csv. Go ahead and download, open it up, and then save it in that correct directory where your project file is stored. Okay, desktop, 662, module 12, diet, save. Okay, and yep, looks like it's saved in there. So let's go ahead and create our new R notebook. Go and delete this unnecessary text. And let's go ahead and name this notebook Factorial ANOVA. And let's create that table of contents per usual. Okay. First things first, we're going to load our libraries. We have a lot of libraries that we're going to be working with today, actually. So go ahead and let me load up some notes here real quick, so I can remember what libraries we're working with. Okay, let's start off with installing some new packages that we haven't used before. So the first one we're doing is install.packages, and this is called the car package. Next is install.packages. This one is going to be the LSR package. And then install.packages. This one will be called the MBESS package in all capitals. And then let's go ahead and just start loading up our libraries. So car, library, LSR, library, MBESS. And then the other ones that should be familiar is library, psych, library, tidyverse, my favorite, and then library, APA, capital T tables. Okay, so let's go, and this is going to take a little while to run because we've got a few packages that we're going to be installing, but let's go and let it go. So installing the car package. There we go. Installing the LSR package. And then the MBESS package. Okay, and now we're loading up our libraries, loading up the tidyverse, and boom. And let's just see, make sure, looks like everything ran successfully. Perfect. I'm going to go ahead and hashtag those out, and I'm just going to press play again so we have some more room to work with. Okay, and let's go ahead and save our notebook. We call the module 12 notebook. Okay. So next thing we're going to do is go ahead and read in the data. Okay, insert a new R chunk. And we're going to name this data set called diet. Use our assignment operator, read underscore CSV. And we're going to read in the diet.csv with a capital DIET.csv. And it'll be saved into a new object called diet in our environment. It has 78 observation of 8 variables. So remember, the main variables that we're going to be focused on today are the gender variable, the diet variable, and the weight loss variable. So before we even get started, I want to go ahead and just start off by factoring those grouping variables that we're interested in. So the two variables that we're going to be factoring today are the gender variable and the diet variable. And then we'll reduce our data set after that. So let's go ahead and do this. Do hashtag factor our grouping variables. And go ahead and insert a new R chunk. Okay, so you remember from last week how we actually used the factor function to actually indicate what our factor levels and labels are, and that's what we're going to be doing again today. So let's go ahead and first we're going to save this into our diet data set. We're going to use the mutate function, and we go ahead and indicate the diet data set, comma, and then we're going to go ahead and create a new variable called gender.f, and that's going to equal the factored form of our gender variable. So we do factor, and then we do gender. So we're changing the gender variable. We're going to be factoring it. We indicate what the levels are. And remember from our data set, we have levels of 0 and 1, in which, so we go C, concatenate 0, comma 1. And then outside of that, we do a comma. And then we set the labels equals, and then C for concatenate. So 0 is female, so we indicate that first, comma. And then 1 is male, so male is the second one. And if we run that, that should run successfully. We have 78 observations of 9 variables, in which we have gender.f, which is just the coded factor version of our gender variable. And let's go ahead and do that one more time, but we're going to do that with the condition variable, or the diet variable. So we're going to do diet, and then mutate. Then we go into indicate the diet data set. We're going to name this diet.f for a factor version of our diet variable equals factor diet, comma. Oh, it's actually going to be a capital D. Okay. And just to keep with consistency, let's go ahead and change this to a capital D too, so we'll have some consistency within it. Hopefully it won't mess me up later. We'll find out. So this one takes on 3 levels, so we do levels equals concatenate 1, comma 2, comma 3. Then outside you do a comma, and then labels, I could spell labels, equals C. Okay, and remember, so our first condition is the control condition, so control. Second condition is the Atkins condition. And our third condition is the Nutrisystem. There are just 3 different types of diets. So we go ahead and run that, and we can see if that runs appropriately for us. Looks like it did. So now we have, which is the diet.f, which is the factored version of our diet variable. As you can see, whenever there's a 2, it goes as Atkins. Whenever there's a 1, it's control. And then whenever it's a 3, we get Nutrisystem. And then you can see the female corresponds to 0 here, and 1 corresponds with male here. So it looks like our factoring did correctly. Perfect. So I'll just run this just in case. All right. And let's go ahead and just select the variables of interest. So we have a smaller variables of interest. So we have a smaller data set to work with. Okay. Insert an R chunk. So we're going to name this diet underscore reduced. And we're going to select from the diet data set, comma. We're going to get the gender.f. We're going to get the diet.f. F with that capital D. We're going to use our outcome variable, which is weight lost. Okay, we do that, we should get a diet reduced data set. All right, we have a diet reduced data set with just the gender.f, the diet.f, and the weight lost that we have associated with it. Okay, so now that we've got that, let's go ahead and get some descriptives that we can look at. So let's go ahead and hashtag calculate descriptives. Okay, we're going to go ahead and insert a new R chunk, and we'll go ahead and use the describe function from the psych package for diet underscore reduced, just to kind of look at what our data looks like. All right, so the main variable of interest that we're going to really be focused on here is the weight loss variable, in which it seems like on average participants lost 3.84 pounds, and the standard deviation is 2.55 pounds. So on average, people are losing 3.84 pounds. But we're interested in getting it based on the diet and on gender, right? We want to see, do people in a diet and do people based on gender differ on this? So we'll go ahead and do some grouping as well. Let's go ahead and hashtag get descriptives grouped by diet and gender. And this is where you're going to see that the factoring really comes into handy when we do this. So we're going to create a new object called diet underscore group. And then do that, and we're going to use the group underscore by function. And then we're going to group the diet reduce data set. We're going to group by gender.f and diet.f. Okay, so we'll go ahead and create that. So if we run that, we're going to have a new data set that's diet reduced. It looks exactly the same, but it's a grouped data set. And then we're going to use the summarize function upon it. Okay, summarize. We're not going to save this into an object, so we diet underscore group, comma, we're going to do mean underscore weight lost equals, which is going to be the mean of weight lost. I think I have that spelled right, and na.rm equals true. If everything worked out correctly, assuming I named all of my variables correctly, we should have, yep, looks like it worked out. Okay, so what we're looking at here is the differences between females and males and how they lost weight in this condition. So, for example, the females in the control condition lost 3 pounds on average. Females in the Atkins condition lost about 2.28 pounds on average, and the females in the Nutrisystem lost a whopping 5.88 pounds on average. And we can see the same thing in the men too. So it looks like the men have a more linear trend, whereas the women actually has a little bit different trend where they seem to lose more weight actually in the control condition as compared to the Atkins condition, whereas men seem to have a different effect on the diets that they do. Okay, cool. So we've gone ahead and done that. Let's go ahead and do some visualizations of our data. And I want to visualize it in a few different ways. So let's go ahead and visualize the data. And we're going to create a few plots. And I think these plots are going to come in handy later when we're actually explaining and interpreting what our ANOVAs are doing essentially. So first plot I want to create is a box plot of just comparing the genders and how much weight is lost overall. So let's go ahead and do this. ggplot. We're going to use the diet reduced data set, comma, set your aesthetic, and we're going to do y equals weight lost, comma, and then we're going to separate it out by color. Color equals gender F. So that's going to give us a box plot that's colored by gender and separated out. So we have 2 total box plots because there's 2 genders. box plot. So if we run that, so it looks like, according to ours, so it seems like the females have a little bit more variability in their scores. Men seem to be losing a little bit more weight as compared to females. At least the mean is showing us that. When they have a little bit less variability as compared to the females. Okay. So now that we've got that, let's go ahead and create another box plot on which we compare our weight loss by the diet type. So hashtag create box plot of weight lost across diet type. And we'll go and insert a new R chunk. And let's go again, ggplot diet underscore reduced, comma, set our aesthetic, y equals weight lost, comma. Now we're going to color it by diet.f plus geom box plot. Okay, and this is where I'm really, shows the beauty of factoring variables. Like I said, factoring variables isn't always necessary, but the reason we factor variables is so we have these nice plots that make a lot more sense when we look at them later. But anyways, as we can see, seems like in general, the control condition had the least amount of weight loss. The Atkins condition had the second most weight loss, and it seems like the Nutrisystem is really exceeding in the losing of weight for diets here. So it seems like that's the best weight loss just from our visualization. Okay, so now I want to do one more box plot, and what we're going to do is actually kind of mix up these into the same kind of box plots. We're going to compare gender across diet type for this, okay? So we're actually going to be using a facet wrap in order to do that. So let's create one more box plot. So it's hashtag create box plots of weight lost across gender and diet type. Okay, let's go ahead and create a new R chunk. The way that we're going to do this is do ggplot diet reduced dataset, comma, set our aesthetic where y equals weight lost, one word, comma, we're going to color it by diet.f. Color equals diet.f. And we're going to go ahead and set it as a geom box plot. And then we're going to use a facet wrap. So facet wrap is a tilde by gender.f. So this create two graphs for us separated by gender and diet type. So we go and press play there. And there we go. And what we're comparing here is see, okay, how did the diets work in terms of females and males, essentially? And really what this is just making a really nice visualization of what's going on here while including the standard deviations and the variances with here. And as we can see, it tells a really different story. Seems like females are really taking kind to the Nutrisystem diet, whereas males seem to be kind of the same across all diet types here, whereas females it seems to be different. And what we're going to be comparing with our ANOVA is we're going to be comparing this box plot, this set of box plots, and the interaction is going to be this set of box plots. And I'll be sure and refer back to them as much as I can when we're running the ANOVA. So let's go ahead and start by conducting our factorial ANOVA. So what we're interested in is, does the amount of weight loss vary across gender and diet type, and the interaction between gender and diet type. So let's go ahead and do hashtag conduct a factorial ANOVA. Okay, and let's go ahead and insert a new R chunk. And really, this is going to seem very similar to how you set up your linear regression models. As we learned last week, it's really just a different way of running a linear regression model and requesting a certain type of output. So we're going to go ahead and name this model. And we're going to save this model. We're going to do LM, so linear model. Our outcome variable is weight lost, regressed on. We're going to do gender.f, f plus diet.f, plus gender.f times diet.f. Now, I realized just now I kind of ended up writing out the entire equation. You can do that entire equation, or you can actually just go ahead and do this, where it's just gender.f times diet.f, it'll give you the same results. This assumes that you want the main effects included in it. I just, from different programming software, so if you're ever using something like SAS or SPSS ever to run like a linear regression model and you have an interaction, you will be required to type out the main effects, but R is pretty smart and knows that you want the main effects included in it. So we'll go ahead and just run it this way. So it's gender.f by diet.f. Okay, then we're going to use the ANOVA function, which is actually from the car package, in which we use a capital A, N-O-V-A, parentheses, we set in our model, which is going to be model, comma, we need to indicate that type equals 3, which indicates we're using a type 3 ANOVA. So if we run this whole thing, we're going to get a new object in here called model, which is going to be just a list of all of our coefficients, and we use the ANOVA function to output it, and output it as a type 3 ANOVA. So we go ahead and press play. Oh, let's see what it, oh, I forgot to indicate my data set. I'm sorry. Comma, data equals diet reduced. There we go. Now it should work. So go ahead and make sure you indicate your data set as well. I forgot to do that. So we go and run that, and voila. So what we're saying is we have this intercept here, right? And that's just saying, is our grand mean different from 0? It's not really too interesting, but yes, it is different from 0. Now we're saying, do our groups of gender vary on weight lost? And it looks like no. So what we're comparing here is this set of box plots saying, does gender vary across weight lost? And no, it doesn't. Then what we're saying is, does diet vary across condition? So the 3 different diets here, and saying, yeah, something's different across these. We don't know where that is. That's where contrast statements honestly come in. We don't know where the difference is, but it's in there somewhere. Okay. And then lastly, what we're saying is, does gender vary? Does the amount of weight loss vary on account of gender and diet? And really what you're saying is, do these two graphs look different from each other? And it's saying, yeah, they kind of do. Something is different. And we can use contrast statements later to indicate where that interaction is. Okay, so we went ahead and do that. And I also wanted to show you another way to output this data set too, which is a really cool way. So we're going to go ahead and do hashtag output the model into an APA styled document using APA tables, apa.aov table. Okay, and we're going to go ahead and do a new art chunk. So what we're going to do is actually output this as a Word document so that it's a APA styled ANOVA table for us. So we use this function called apa.aov.table. We set in our model, so it's just called model here, comma, we set a file name equals, if you'll remember that this is pretty similar setup to when we set up those APA style correlation tables. And it's going to be, we'll name it model.doc, comma, we want our conf.level equal to 0.95. Otherwise, it's going to give us a confidence level of 90%, and we want to set it so that it's 95%. So if we run this, voila, we get the same exact output here, but looks a little bit differently. However, if we go to our, as you can see, a new thing called model.doc opened up. If we go into our project file, so it's module 12, we have that model. We go ahead and open that up, and voila, look at that. We have an APA styled ANOVA table. You can just change the table number if you want to, and it tells you, even gives you notes. It says fixed effect notes of results using weight loss as a criterion, so you can change that to a more reasonable variable name, and you can change these to actual variable names too. So it's a really nice feature that APA tables once again brings to us, so that we don't have to do all this formatting in Word for us. Okay, yeah, so that's pretty much it for running the ANOVA. Now what I want to do is we're going to teach you how to get the 95% confidence intervals for the ANOVA as well. So we're going to do that, and then we're going to create an interaction plot, and then we're going to set up our contrast. So Now you might say, okay, well, what about my 95% confidence intervals for my actual model? So let's go ahead and do it. So let's do hashtag get 95% confidence intervals. Insert new R chunk. In order to get the 95% confidence intervals, we do ci.pvaf from the mbest package. Okay, and what we need to do is indicate some things for this. So let's go ahead and let's get 95% confidence intervals. We use the second level header and we'll say for gender.f. So in order to do that, we just have to specify some criterions for this. So the first thing we want to do is get for the gender.f, we need the f value. So f value equals, and that's going to be 0.39, 0.39, comma, and we need to give it the degrees of freedom, so it's going to be degrees of freedom dot 1, so our first degrees of freedom, which is equal to 1, and then the df dot 2 equals 72, because it's our degrees of freedom error, it's our degrees of freedom 2, so equals 72, and then comma, what is our n? Our n is, look at this, 78 observations, n equals 78, comma, and then conf.level equals 0.95. That's saying that we want a 95% confidence intervals. And then what we do that, and voila, we have a lower limit of 0. So it's just saying that it's below 0 or below 0. And our upper limit is 0.025. Okay, and then we can do the same thing for the diet.f and the interaction between the two as well. And we'll go ahead and do that too. So we'll do hashtag for the diet.f. Okay, and then we'll go ahead and insert a new R chunk. So we'll use the ci.pvaf. So again, let's set the f.value equals, so we go ahead up here, f.value for diet.f, is 10.14, comma, we want the df.1 equals, so what is our degrees of freedom here for diet.f? It is 2, then df.2 equals, and our df.2 is 72, should be the same across all of them, comma, our n equals 78, comma, and our conf.level equals 0.95. And here we go. And there we go. We get the probability limits for this as well. So we have our probability lower limit is 0.025, and our greater upper limit is 0.025. Or I'm sorry, it's 0.06 and 0.35. There we go. Sorry, these are the, it's saying it's covering 0.025%. So it's 0.06 and 0.35. And then we can get the same exact thing for our gender by diet reduced data set as well. So let's do that one more time, then go for hashtag gender.f by diet.f. And so we'll go ahead and insert a new R chunk, and we'll go ahead and do ci.pvaf, and then do f.value equals, so our f value for this was 3.79, comma, df.1 equals 2, I believe. Yep, it's 2. df.2 equals 72, comma, n equals 78, comma, conf.level equals 0.95. Go ahead and run that. Oh, what did I do wrong here? Oh, CI. Oops. CI. I'm sure some of you saw that coming. There we go. And then we get our confidence intervals there too. So go ahead and press save. Okay. So the next thing we're going to do is we're actually going to go ahead and create an interaction plot. And really what an interaction plot is just looking at these, but looking at the slopes between each of these mean values essentially. So it's a little bit, I know Kevin taught you how to use it, create an interaction plot via interaction.plot. However, we're going to be using just standard ggplot to create this. So let's go ahead and do hashtag create an interaction plot. Okay, we're going to go ahead and insert a new R chunk. All right, so there's a few steps associated with this. So the first thing we're going to do is we're actually going to write over our diet groups, and we're going to create another group thing. And we're going to do group underscore by. It's going to be diet reduce. This is the just that we're grouping. Now we want it to be grouped by gender.f, comma, and diet.f. So we're going to be having a group by gender.f and diet.f. Then we use the diet. We're going to create a new object called diet.graph, diet underscore graph, I'm sorry, in which we are going to create, this is setting us up for an interaction plot in a little bit here. We're going to do summarize. We're going to do diet underscore group, comma, we're going to do weight lost equals mean weight lost. So we're going to get the mean of it. And remember, think about it this time. We're actually going to be creating a new object called diet undergraph, which is we're going to utilize our summarize output later. And just to be safe, I just want to do diet underscore graph. Use our assignment option. We're going to use a function called ungroup. And that's just going to make sure that we don't run into any troubles later. We're going to ungroup our diet graph thing because it's I have a fear that it's grouping this and then grouping into here, and it might give us problems later. So I'll show you what's going on when we run all three of these lines. So let's go ahead and run all of this. Okay, don't worry about that. That's fine. That's an okay to have that argument there, or that message there. Then we have the diet graph, which is all they did is get the mean of weight lost by gender and diet, essentially. So this is what we created earlier, actually, but we saved it to an object now. And now we're going to utilize this object to create an interaction plot. So let's go ahead and just do it in the same thing. ggplot, parentheses, we use the diet underscore graph object we just created, which is meant to create these interaction plots. We use AES, parentheses, x equals gender.f, comma, y equals weight underscore, weight lost, comma, and we're going to color it by diet.f. Okay, and go ahead and just do a plus sign. And we're going to use a geom underscore line for this one. Then we're going to do AES group equals diet.f. Okay, and that's saying we want our lines to be grouped by diet.f. So that's a pretty essential thing that we have. So we're having it colored and we're having it grouped. We could do it without the color, but it just makes it look a lot nicer for us. Then, just to make things look a little bit nicer, I'm going to do scale. I did a little bit of looking ahead at my graph earlier, but we're going to do scale underscore y continuous. And then we're going to do limits equals concatenate 0, 6, and that's just going to set our y-axis limits to 0 and 6. So the minimum is going to be 0 and the maximum is going to be 6. I did a little bit of work beforehand to just kind of evaluate what the best looking graph is, but that's what that scale y continuous does. And let's go ahead and set some labs for us too. So labs, so title equals interaction plot, comma, subtitle equals weight lost by gender and diet. Okay, so if we run all this, it should work out fine. So let's go ahead and press play. And here we go. Okay, so we've got this new graph That's the interaction between our group. So you can see that there's, okay, yeah, clearly these lines are all have different slopes to them. The Nutrisystem seems to work a lot different for females versus males. The control group, it works a little bit better for males as compared to females, and the Atkins seems to work better for males as compared to females, is what we're looking at here. And I'm going to tell you a secret. So really, these lines are really just the slopes between these. As you can see, is really all we created. But we just used a really fancy ggplot method in order to do it. You can also use Kevin's interaction.plot method in order to create interaction plots as well. But ggplot's a little bit more flexible, and you can make like more designs with it if you want, and kind of make it for more publishable material too. But there we go. So we went ahead and created an interaction plot. And now what we want to do is set up our contrast and see which of these interactions is significant here. And what we're going to be doing is comparing the slope of the control group to the slope of the Atkins diet and the slope of the Nutrisystem diet. So let's go ahead and go hashtag set up our contrast. So you remember from last week, this was a little bit, I hope it wasn't too intense, but a little bit intense to do this. The first thing we're going to do is go ahead and create our gender contrast. All right, so we're going to name this GC1. Use our assignment operator and do our concatenate. We want to compare females to males. And I'll let you know a secret. You don't technically have to do this contrast if it's a binary variable. The summary.lm function will kind of do it for you, but I think it's good practice to do it. So we'll set it up for our gender variables where we'll be comparing females to males, and then set it up for our diet variable, .f variable. So let's go ahead and set this. Set up contrast for gender .f variable. Remember, we're going to be setting up these vectors so that we can add them into as an attribute for our variables. So we're going to have two total contrasts for our diet.f variable. So let's go ahead and do DC1, which stands for diet contrast 1, is C. We're going to do 1, so that's for the control variable, -1, 0. So here we're going to be comparing the control group to the Atkins group. And we'll just do DC2, which is going to be the concatenate, which is going to be 1, 0, -1. And here we're going to be comparing the control group to the Nutrisystem group and saying, are the slopes different there? Then we go ahead and remember, we use contrast parentheses. So this is going to be the diet underscore reduce data set. We use a dollar symbol, dollar operator, and then the gender.f, and then we're going to set this into our gender.f, and we're going to name this GC1. No need to use a cbind function, but for our next one, we will have to use a cbind function. And we're going to do contrast parentheses diet underscore reduced $sign operator diet.f, and we use our assignment operator. Now we're going to use the cbind. We're going to cbind DC1, DC2. All right, so let's go ahead and play that. It should all work out. So now if we get the structure of our diet reduced data set, we should see these contrast statements associated with it. There we go. So gender has a contrast statement associated with it, and diet.f also has a contrast statement associated with it as well. Weight loss, however, does not have that. Then we go ahead and we run that summary.lm function. So let's do hashtag summary.lm. Okay. To analyze our contrast. Okay. I'm going to insert a new R chunk. And then it's simply, we do model underscore contrast. We're going to name a new object. Use our assignment operator. We're going to do LM. Now we're going to do weight lost regressed on. We do gender.f star diet.f. And that's going to run a new ANOVA, a new linear regression model on our newly created variables with that contrast attribute associated with it. Then we do summary .lm and then model comma contrast. Let's spell it right. There we go. So that's going to get summary model of our contrast. And we press play. Once again, I forgot to indicate my data set. Data equals diet underscore reduced. Okay, this should work now. So we go ahead and run this. Oh, there we go, diet.f. Okay, as you can see, I'm making some errors here, but here we go. Now it runs. Okay, so what do we have here? So we have our intercept, which you remember was the grand mean before, and we're just saying, is that different from the attribute of 0, or is that different from 0? And yes, it is. It's not too much of interest to us. Then we have this gender F1, which is comparing our males to our females. Remember, we set it as -1 to 1. So -1 and 1, and we're saying, is there a significant difference between males and females? And no, there's not a significant difference between males and females. Then we're saying, okay, is there a difference from our first contrast setup for diet, which, as you recall, was the control group compared to Atkins? Is the control group significantly different from Atkins? And we're saying, no, it's not significantly different from Atkins. And if we scroll up to our other box plots, what we're comparing is this box plot to this box plot, saying, is there a significant difference between the two? And it's saying, no, there isn't. Next, we're going to compare this box plot to this box plot. We're saying, is there a significant difference between the groups? And it's saying, yeah, there's a significant difference between the control group and our Nutrisystem group. Saying, yeah, it looks like on average, people lose more weight in the Nutrisystem group. Great. Okay. Now, what we're comparing here, and summary.lm knows that you want to look at the interactions already. We're saying, is there a difference between male and females in the way that they experience the control group compared to the Nutrisystem group? I'm sorry, to the Atkins group, because this is our first comparison. So what we're saying is this line different than this line? And it's saying, yep, there are different slopes. There's definitely an interaction involved here. Then we're comparing males and females on their terms of the diets between the control group and the Nutrisystem group, and it's saying, yep, there is a difference between these lines. So it's saying, is there a difference between this line, the slope of this line, and the slope of this line, essentially? And it's saying, yep, there's definitely a difference between those two. Males and females seem to experience the control condition and the Nutrisystem condition differently from each other. And that's all that there is to factorial ANOVAs that we need to discuss today. So I know that contrasts are sometimes a little bit confusing. I hope those are a little bit more understandable. But remember, we're adding in these attributes to our contrast statements, into our variables as a contrast, essentially. So whenever you're ready, you can go ahead and get started on the assignment. So if you go to home, go to modules, then go to module 12 lab, and there's a module 12 lab activity for you, and we'll be using the sleep data set for that. All right, well, thank you so much. I look forward to seeing your assignments.